Hello everyone. In this session, we are practically going to implement the logistic regression model without leveraging any of the functions or classes associated with scikit-learn library. Okay, before we begin with this particular coding exercise, let us try and understand little in detail about what logistic regression is and what are the different steps that are involved in the gradient descent process or the optimization process as a whole. So these are four different steps, and there is an additional step which is step number 5, that is to repeat step number 1 to 4 iteratively till we obtain convergence, right? So the very first step here is going to be initializing the weight vector as well as a bias. So we know that Z computation here is going to be the linear combination of inputs, which is W transpose X plus B. And this is what we have done for linear regression. For logistic regression, we are going to pass this as an input to your sigmoid function, which is sigma of Z, which is given as 1 by 1 plus e to the power of minus Z. This is going to produce your output in the range of 0 to 1 values, which can be implied as predicted probabilities here. So the binary class problem that we are trying to solve, the output of which is going to be in the form of predicted probabilities, which is output of your sigmoid function here. So yi hat is going to be 1 by 1 plus e to the power of minus z, where z is a linear combination of inputs, which is w transpose x plus b. And here we are going to consider a loss function as log loss or binary cross entropy loss, which is given by this equation. We already have covered about the cross entropy loss in one of our earlier sessions, the link for which I'm providing here on the top. So this loss function has to be differentiated with respect to the different model parameters w and b here. These are the equations that I obtain after applying differentiation to this loss function with respect to the corresponding model parameters. We are going to make use of these equations while finding the derivatives or while implementing the fit method of your logistic regression class. And finally, whatever derivative value that you compute are now plugged into this parameter update equation. And we repeat the whole process iteratively till we obtain a particular value of W and B where you observe minimal loss. And that's the whole optimization process, isn't it? Now let's get back to this particular code where we have imported specific modules from scikit-learn, that is to load this particular dataset. We also have imported standard scalar, which is used to standardize the given data, train and test partitioning function, which is train test split here. So I have unpacked the data into X and Y here. Using the X and Y that we have determined in the previous step, we're now going to perform data partitioning, which is given as X train, X test, Y train, and Y test. We are now going to make use of this particular object called scalar in order to transform or standardize the given data, standardize the given X data. We are fit transforming on X data, we're just transforming on X test data. That's all. So with whatever we have done so far, we're now going to write code for logistic regression.py module. So first I'm going to import numpy as np, because this is going to help us perform certain mathematical operations while implementing fit and predict methods here. So the class here is going to be logistic regression. So the very first method here is going to be the init method, which is a constructor, where I'm going to define the parameters that I'm planning to attach to the model object itself. Here it's going to be learning rate, setting a default value of 0.001, number of iterations as 1000, weights and bias as none. Okay, the number of iterations here typically denotes the number of iterations that we are planning to conduct in the optimization process. Okay, so self.lr is going to be lr itself. I'm also going to assign n iters to self.n iters, and later going to assign weights to self.weights, and self.bias is going to be bias itself. Now let's look at implementing the fit method, which accepts two different parameters, x and y. So generally we use x train and y train, that is a train data, while trying to fit the model object. Okay, so for whatever x data that we are perceived, we're now going to understand the number of samples from x data and number of features by using x.shape here. Let us initialize the weights and biases, because that's the very first step of the optimization process. So np.zeros is going to help me initialize all the weight vectors with zeros here. The number of weights will be same as the number of features within your input data. So self.weights is what I am going to assign the 0 vector to. Subsequently, self.bias here is going to be value of 0. Now I need to generate the predictions. Generate predictions. So generating the predictions, first I need to compute z value here, which is going to be the dot product of x and y, sorry, x and w. So dot product of x and w plus the additional bias term that we have initialized in the previous step. I'm now going to consider the z as an input to the sigmoid function so as to generate the vibrates. I'm calling this as vibrates here. So we do not have the sigmoid function yet. So let us define a global function called sigmoid, providing a particular parameter as z here. So 1 by 1 plus exponent of minus z is what the sigmoid function is. You can very well verify this particular function, that is 1 by 1 plus e to the power of minus z. So 1 by 1 plus e to the power of minus z is what we have computed within this function. I'm just going to return it as is, that's all. So we have generated the vibrates, but this has to be for all the iterations that we are planning to conduct. I'm going to create a range object by using niters, which is self.niters. So for every single iteration, we are now going to compute what z is and what the corresponding y predictions are. Okay. So along with this, we are also supposed to find the derivatives of loss with respect to w, derivative of loss with respect to bias here, which is implementing these different equations that we are observing. So now we simply go about finding the dot product of x transpose, whatever we are observing in that equation, x transpose and weights here. Okay, I need to multiply this whole term with 1 by n. Right? So I'm just going to multiply this whole term with 1 by n. 1 by n, n here stands for number of samples. The number of samples that we have identified in one of the initial steps within the fit method. Okay. And this is not going to be weights. I'm sorry about that. Here it should be the difference of vibrate and y. So if you look at this equation carefully, it's going to be the difference of vibrate and y. So let me compute the difference, which is going to be vibrates minus y. That's it. Let me copy this whole statement, paste it here again. Just take the summation of the differences that we are observing, and that's all. Take the summation of all of the differences that you observe between vibrates and y's here. And then again multiply it with 1 by n, as you can observe for this particular derivative of loss with respect to b equation. That's what we have implemented here. That's it. So we have computed the respective derivatives. We're now going to update the respective model parameters. The self.weights is going to be self.weights minus theta times the derivative that we have computed in the previous step. Same is the case with bias. So self.bias minus self.lr, which is learning rate, times the derivative that we have computed in the previous step. So let me put a parenthesis so that we are giving priority for the multiplication here. So once the weights and biases are updated, at the end of 1000th iteration, because 1000 was a default value for n iters, at the end of 1000th iteration, you have the right values for your weights and biases. I'm going to make use of those weights and biases for my predict method. So the predict method typically involves the test data. So now let me implement the predict method, which is going to be the dot product of x and weights, add a bias term to this, which is nothing but z here. So in order to compute vibrates, I'm going to consider the statement as is. I'm going to return the vibrates as such. There we have implemented the predict method as well. So we have written a lot of code. We have defined this particular class called logistic regression with both fit and predict methods. Now let's import that particular class from this module called logistic regression. So logistic underscore regression, import logistic regression. Let me rerun, or let me restart the kernel first so that whatever code that we have written is in effect now. Let me rerun all the cells and finally look at creating this particular model object using this class that we have defined. And model.fit is going to help me fit the object onto the train data, which is x train and y train. Model.predict, apply it onto the test data so as to generate the test predictions here. So we now have the test predictions. So whatever test predictions that we are observing are nothing but the probability values. So in order to convert these probability values into the predicted labels, we are supposed to write a simple list comprehension, right? So we need to iterate over each of these predictions. Pred for sorry about the typo, pred for pred in test underscore predictions. If pred is going to be lesser than or equal to 0.5, then I am going to classify it as 0, else I am going to classify it as 1. These are the predictions. These are the predicted labels. I can call this as spread labels. So let me make use of this spread labels and actual y values. Use crosstab here. So pd.crosstab. I'm going to provide actual y test values and the prediction labels that I have deduced in the previous step so as to come up with this confusion matrix. So this is a confusion matrix, isn't it? I'm calling it as CM. So this object CM is going to help me generate the accuracy metric. So I'm referring the diagonal elements, taking the sum of all of the diagonal elements, and finally dividing with the total number of observations that I have in my test set so as to deduce the accuracy. The accuracy turns out to be 94%. It's pretty decent enough. Okay. But again, if you observe this particular module closely, we have not implemented the convergence yet. So we do not know what is the right n iters value here. So I am leaving this as an exercise to you in order to make some changes to this code so that you are implementing the convergence. You are stopping this iterative for loop at a particular point where you're not observing any incremental change in weights and biases. Okay. And finally, determine what could be your right weights and biases that you can leverage in order to generate your final predictions, which you can consider later for documenting what the confusion matrix is and what the accuracy is and so on. So I'll leave it as an exercise again on computing what recall rate and precision rate here by using this confusion matrix here. Okay, I believe we have pretty much understood on how you can implement the logistic regression model right from scratch. That is without leveraging the existing classes specific to scikit-learn library. Okay, please subscribe to this channel for more such updates. Thank you.